So we're going to go back and revisit some content we looked at back in Foundations and Pre-Calculus 10, and that's regarding radicals. Keep in mind that a radical is anything that has a root sign in it. So here just below we have an indication what a typical radical would look like. This piece in blue is called the radicand. Most commonly it'll be referred to as what's under the root sign. We have the actual root sign, and we have the index. Each of these things is going to be come to play in different contexts as we go through. Something else that we will see a bit later on is like terms in terms of radicals. In order to be like terms with radicals, we have to have the same index and the same radicand. So that's why here 5 root 7 and negative root 7 would be like. They're both square roots, square root of 7. Here we have a couple more complex ones, but they are both like because the index is 3 and we have 5x squared as the radicand. We have two unlike radicals over here. This set is unlike because we have root 5 and root 3. And this set here is unlike because we have different indexes. One has an index of 4, one has an index of 5. So moving on to actually working with these radicals, one of the first things we're going to have to do is to convert an entire radical to a mixed radical. Now when I say an entire radical, all 4 of these qualify as that because we have nothing outside the root sign, we have no coefficients. A mixed radical would be something such as 2 root 5 as we saw before. In order to do this, we need to take each radical and break it down. So if we look at A, we need to break down 200 into its prime factorization. Now we can do this with a factor tree, but that does take up a lot of space and is a little bit more complex than it needs to be. So we're going to go ahead and do it step by step. So first of all, knowing prime numbers is key to all of this. Prime numbers would be 2, 3, 5, 7, 11, and so on and so on. So you first need to ask yourself, can you divide this 200 by 2? Well, yes you can. So another way of saying 200 is if we divide it by 2, 200 is the same as 2 times 10. Sorry, 2 times 100. As we keep going, so we have the 2 that we took out before. Now look at 100. Can we divide that by 2? Yes, we can. And that 100 will be 2 times 50. And we're just going to repeat this process until we get everything down to prime factors. So we have the 2 times 2 already. Looking at 50, we can divide that by 2, and 50 is the same as 2 times 25. So we have 2 times 2 times 2. Now, looking at 25, that one is not divisible by 2, so we'd move on to the next prime number, which is 3. It's also not divisible by 3, so keep moving on until you find one. 5 is the next prime, and 25 is divisible by 5. So out of 25, we would get 5 times 5. Now that we have this down to prime factors, we can start to look at these things and group them off in ways to take pieces out. In order to do that, we need to look at the index. And the index of every single one of these roots is a 2. It's kind of like an exponent of 1 in that it's never written, but it's always assumed to be there. So if you don't see an index, it is a 2. Which means when we're looking at this prime factorization, we need to look for groups of 2 identical items, identical factors to take out. So we have a group of 2 2s, we have a group of 2 5s, so we can rewrite this as separate radicals. And for the moment, I'm going to do that. There's my group of 2's. I'm going to put my group of 5's next. And then I have this single 2 that's left over. Now, this next step I'm not going to be doing every time. It's just an illustration of why this works the way it does. If we put together those roots again, so that first one was the square root of 2 times 2, which would be the square root of 4. Square root of 5 times 5, also known as square root of 25. And square root of 2, which is what it is. Well, we can actually simplify these now, as we do have a couple of perfect squares. The square root of 4 is 2. Just 2, not the square root of 2, just 2. Square root of 25 is 5. And the square root of 2 isn't reducible. Looking at this, now we have this 2 times 5 that have come outside, which we can multiply together, and this, not needing brackets anymore, would be the same as 10 root 2. So this is the method we're going to use to take an entire radical and convert it to a mixed radical. Sometimes this step here and this step here, and even to a point this step here, could be omitted if we can see the patterns going on and we know the process of getting from point A to point B. Just going to clear out the page to do question B. B is now a 4th root. That is going to have an impact when we go to take groups out. But we now have a variable in here. It's c to the power of 9, which literally means we have c multiplied by itself 9 times. That exponent is just a good shorthand. But in this circumstance, it actually doesn't help a whole lot. Looking at this now, we need to look for groups of 4 that we can group off, and we have 4 C's here. We have another 4 C's here. Those we could break out as separate radicals, or we could just skip ahead and know that this group of C's we can take out, and we'll have a C. This other group of C's we can take out and have a second C. And we had one C that we couldn't group off, so we will have the 4th root of C from that one. So where did these come from? That C came from here, that C came from here, and that C came from here. One last step of simplifying, we have C times C outside the root. That is the same as C squared. And we have the 4th root of C. This example here actually leads me to another point. When we have exponents mixed in with indexes, the squared exponent and the 4th root index, just be careful that you're writing this clearly and you know that the 2 is an exponent and it's not an index of, let's say, 24, or likewise that the 4 is an index and it's not an exponent of 24 as well. If you have to leave a little bit of space or exaggerate that notch to make that happen, that's fine, as long as it's clear what's an exponent and what is an index. So example C, clear the page just to do it. Now we have mixed number and radical, so it'll be a little bit more work, but it's the same general process. Dealing with the 48, we need to prime factorize it. We can divide 48 by 2, which would be 2 times 24. Now we can at this point laid out 5y's multiplied together, but since we're going to be doing that for a couple of steps, I'm going to save that for the end, just to shorten this up, make it a little bit quicker. We could lay out y times y times y times y times y now, but again, it's just going to take up a little more space and a little more time. So keep prime factorizing. We have 2. Looking at 24, 24 is divisible by 2. It's 2 times 12 times the y to the 5th. Now you don't need to always write out every step of the prime factorization. If you can see a couple of steps in, you can go ahead and do it that way. But just know that it does need to get fully prime factorized. So we have 2 times 2. Looking at 12, it's also divisible by 2. It would be 2 times 6. Keep going on the prime factorizing. We have 2 times 2 times 2. 6 is divisible by 2. It's 2 times 3. And just taking a pause here before I write down times y to the 5th. If I look at my factorization now, this is fully prime factorized. So this is the last step in breaking down of the 48. I am going to go and I'm going to write down my 5y's multiplied together right now, since I know this is the last step of the prime factorization. So we've got this all factored out. Now we can take a look and grouping things off. We need to figure out what size of a group we need. Since there's no index in that notch, it has to be a square root. It means we're looking for groups of 2. So I have 2 2's, 2 y's here, 2 y's here. Those will come, they will take out, they will come out, become coefficients on the root. So outside, we're going to have 2 times y times y. We have some leftovers under that root. We have a 2 times 3 times y. Simplifying this out, outside the root, 2 times y would be the same as 2y squared. Under the root, 2 times 3 times y, same as 6y.